Good morning, students. So the topic for the day is operational amplifiers. We This is some basic topic which is required for the further applications of the operational amplifier. We'll just quickly go through them and see what's next. Well, so this was the basic symbol of the operational amplifier. That is, it has an inverting terminal, it has a non-inverting terminal designated as minus, plus capital A. What does capital A mean? It means the open loop gain. That is the gain of the amplifier. Plus VCC is the positive supply of it. Negative VEE is the negative supply of it, and the output is measured over here at this terminal. So operational amplifier, two terminals, non-inverting terminal, positive, inverting terminal, negative, open loop gain A, and the output V out over here. Now the op-amps with feedback. So what is feedback? Feedback means that essentially a part of the output will be given back again as the input. So there are two configurations, again inverting amplifier with feedback and non-inverting amplifier with feedback. So inverting amplifier means we will be giving the input signal to the inverting terminal, and for the non-inverting amplifier the input will be given to the non-inverting terminal. Okay. Now, for an op-amp, the voltage at the inverting input terminal is equal to the voltage at its non-inverting input terminal. This is actually a theory which is assumed by us. So, what happens is there is no short or there's no connection between these two terminals, that is the inverting and the non-inverting terminal, but virtually, that is something which is not in real, they are in short with each other. As a consequence of these, what happens is whatever voltage appears at the negative input over here is the same voltage that appears over here at the positive input. So this concept is called as the virtual ground concept or virtual short concept. And also I would like to point that the feedback. So what is the feedback? I said feedback is where a part of your output is given back to the input, right? So this is your feedback path. From here, V out, a part of the V out through this feedback resistor RF is given at the input over here, okay? And R1 over here is your bias resistor, and Vi is your input signal which is given to the inverting terminal, right? Now, having understood what the virtual ground concept is, what do you think would be the voltage over here? See, since this terminal is directly connected to the ground, that is at zero potential, that zero potential or zero voltage will appear at this positive terminal. Okay. Now, since these two terminals are internally short, that same 0 volt will appear at this terminal as well. I hope it's understood. So virtual ground means the positive and the negative terminals are connected together. Whatever voltage appears over here will be the same voltage that appears over here as well. So putting that in words, in the above circuit, the non-inverting input terminal is connected to the ground. I explained that over here. That means 0 volt is applied at the non-inverting input terminal of the op-amp. And the virtual short concept says that the voltage at the inverting input terminal, that's the other terminal of the op-amp, will also be 0 volts. I hope this is clear. So virtual ground concept or the virtual short concept, the feedback resistor and the bias resistor. So this slide is important. Please students go through this thoroughly. Let's move on. The inverting feedback. So the inverting feedback, again, where is the input given? The input Vi is given to the inverting terminal. The non-inverting terminal is grounded. You know this already. Whenever we talk about any of the configuration, say inverting, input is given to the inverting, and the other terminal non-inverting will be grounded. Feedback, so RF and Ri. This path is always there in the op-amp circuits, okay? Now, the nodal equation at the terminal, which terminal? We are talking about this terminal now. We have to analyze the circuit. So, we consider this point or this terminal and we apply nodal analysis. So, what is nodal analysis? It is nothing but the current relation, the KCL. So, think about how the current would be passing from Vi. The current enters into Ri, goes up through RF and then leaves as V0 over here. So, this is the path. From here, goes up to RF and out, V out over here. Here there is no current flowing. Anyway, this is at zero potential. Okay. So if the potential over here is 0, The potential over here is 0, so 0 volt over here at this end of the resistor and Vi at this end of the resistor. So 0 minus Vi divided by Ri will be equal to the current in the first branch. Now tell me what will be the current over here. So again 0 voltage over here. The other end of resistor Rf is connected to V0 volt. So 0 minus V0 divided by Rf will be the current in the feedback resistor. So that will be the second current. And again, these two currents are entering into the junction. Since no current is leaving, the sum of these two currents will be equal to 0. So this is the nodal equation. Again, for nodal equation, remember that we consider the potential over here to be 0 volt. So 0 minus Vi by R1, 0 minus V0 by Rf. The sum of these two currents is equal to 0. Okay. Now simplifying the equation, what do we get? We get minus Vi by R1 is equal to, taking this to the other side of the equal to, it becomes V0 by Rf. Now what is the output voltage? That means output voltage is equal to minus Rf by R1. Just taking this to the other side of the equation, and the ratio V0 by Vi. Now this is not supposed to be Vt, this is Vi, it's a misprint. Please understand that this is Vi. So V0 by Vi will be equal to minus Rf by R1. You already know what is V0 by Vi, the ratio of the output voltage, that is V0, and the input voltage Vi is nothing but the voltage gain, or simply we call as the gain of the amplifier, that is output by input. Therefore, the gain of the inverting amplifier is equal to minus Rf upon R1. Okay, you have to remember this. This is very important equation in case in the exam you get some numerical based on the negative feedback or the inverting amplifier feedback. You might be given Rf and you might be given R1. You might be asked to find out the gain of the inverting amplifier. There's a simple equation for that. Okay. Now there's a negative sign, which means that there is a phase difference between the output and the input. That phase difference is depicted by this negative sign over here. Let's move on to the non-inverting feedback. Now what is non-inverting feedback? Non-inverting feedback means the input will be given to the non-inverting terminal, that is over here Vi. And since it's a feedback, the path remains the same, that is Rf and R1. What about the input at the non-inverting terminal? The input at the inverting terminal will be grounded because we are using the non-inverting configuration. So the terminology is Vout for output voltage, Rf for feedback resistance, R1 for the bias resistance, and Vi for the input voltage. Now, a non-inverting amplifier takes the input through its non-inverting terminal and produces its amplified version as the output. Okay, this is the definition of your non-inverting amplifier. Now, as the name suggests, the amplifier just amplifies the input without inverting or changing the sign of the output. Okay. In this equation, in this circuit, we'll have to apply the nodal analysis also. But before that, in the above circuit, input voltage Vi is directly applied to the non-inverting input terminal of the op-amp. And so what about the voltage at this negative terminal? If we apply the virtual short concept, which we just explained previously. So Vi over here, same voltage will appear at this terminal, right? So the voltage at the inverting input terminal will also be equal to your Vi. So the voltage at the non-inverting input terminal of the op-amp will be Vi. And we use voltage division principle. What is voltage division principle? I'll quickly explain. Let's get back to the circuit. So say suppose you want to find out the voltage across R1. You want to find the voltage across R1 and you are knowing that Rf and R1 are connected in parallel. So the voltage division rule says that the voltage at this R1, across this R1 is equal to R1 divided by the sum of these two resistances. Similarly, if I want to find out the voltage across Rf, it would be this resistance Rf divided by R1 plus Rf into the input voltage. So applying the voltage division rule, what do we get? We get V1. What is V1? V1 is the voltage at this terminal, that is at this point. It is of course Vi, but we are also telling it this as V1. So V1 is equal to V0, that is the output voltage, into R1 by R1 plus RF. This is the voltage division rule that I was talking about. R1 by R1 plus RF. Now, so the virtual short concept, the voltage at the inverting input terminal of the op-amp will be the same as that of the voltage at its non-inverting input terminal. Extending that to this equation, what can we write further? We can write V1 is equal to Vi. Yes. What is V1? V1 has already been found out to be equal to V0 into R1 by R1 plus RF. Okay. So again, if I want to find out the gain from this equation, what do I get? We can get V0 by Vi. What is V0 by Vi? It is nothing but the output voltage divided by the input voltage Vi. Okay. Again, in the numerator over here, there's R1, there's an R1 over here in the denominator. We can cancel them, and what do we get? We get 1 plus RF by R1. So what is the gain? The gain becomes 1 plus RF by R1. Now the ratio of the output voltage V0 and the input voltage Vi, or the voltage gain or gain of the non-inverting amplifier, is equal to 1 plus RF by R1. So again, in the exam, if you get a numerical to find out the gain of the non-inverting amplifier, if RF and R1 is given, you can easily find out, right? Is there any negative sign in this? No, there is no negative sign. So the gain of the non-inverting amplifier is having a positive sign, which means that there will not be any phase difference between the input and the output. Okay, so I hope these two configurations are clear to you. Yes. Now, a very simple concept of voltage follower. It's an extension of the previous two things that we have studied. So what is a voltage follower? It's an electronic circuit which produces an output that follows the input voltage. Basically, it's a special case of a non-inverting amplifier. So what's a non-inverting amplifier? The input is given to the non-inverting terminal, keeping the inverting terminal grounded. Okay. Now, how does this become a special case? To make this, you have to consider the feedback resistor RF as 0 ohms and the value of resistance R1. So this R is missing. It's R1 as infinity ohms. Then a non-inverting amplifier will become a voltage follower. That is, RF is kept as 0 and R1, which was supposed to be over here, becomes infinity. So if it is infinity, there's no point of connecting that. Okay, so there is no existence of that resistance. So now just think about it. If V1 is given to the non-inverting terminal, using the virtual short concept, V1 appears at the negative terminal. That same voltage appears as your output. So what is output voltage? It is the voltage at the inverting terminal, which is the voltage at the non-inverting terminal, and it is the voltage which is given as the input. So Vi is equal to V out. Okay. So in the above circuit, the input voltage Vi is directly applied to the non-inverting input terminal of the op-amp, and the voltage at the non-inverting input terminal of the op-amp is equal to Vi. Yes. The output is directly connected to the inverting terminal of the op-amp because there is no feedback resistance, that is 0. So hence the voltage at the inverting input terminal of the op-amp will also be equal to V0. So according to virtual short concept, the voltage at the inverting input terminal of the op-amp is the same as that of the voltage at the non-inverting input terminal. Okay, that is V out is equal to Vi. So this is a simple voltage relation for the op-amp which is connected in the voltage follower. Thus, the gain of the voltage follower is equal to 1. Why? V out by Vi will be equal to 1. So it is 1, unity. Both output voltage and input voltage would be the same. That's why it's called as a voltage follower. I hope this topic is clear to you. Okay. Thank you, students.